All right, so welcome back, everyone. Thanks for coming along. There is a 2521 revision session happening right now, but it's from 2 to 5, so you'll still have time to attend if you want after the lecture. Right, and I expect this lecture to be a bit lighter, so we won't be here the whole 2 hours. All right, and this is also the last content for the course. Next week's lecture will probably only have one lecture, and it will be about with course revision and also the final exam. All right. So today's lecture is about tries, right? And just to motivate why we're talking about tries, many applications require us to search through a set of strings. So some examples of that are predictive text, which I'll talk about in a second, auto completion, approximate string matching, and spell checking. So these are just some examples. So what is predictive text? So if you've used a phone with a keypad before, and maybe you have, maybe you haven't, then in order to type a word, right, each of these keys can represent multiple different letters, right? So the 2, if you press the 2, that could mean A, B, or C. When you press 3, that could mean D, E, or F, and so on. So in order to type a word, you type or you press the buttons containing the letters that in the word that you want to type, right? So for example, if you want to type the word good, then you would press the keys 4, 6, 6, 3, right? So that is called also the process of predicting what word you are typing based on what keys you pressed is called predictive text, right? Because the sequence of keys 4, 6, 6, 3 doesn't necessarily just refer to the word good. It could refer to other words like home or hood or hoof. Right, so one problem is, given a sequence of key presses, what are the possible words? Right, so another example of an application is auto completion. Right, so you're given the start of a word that's being typed, what are the possible words, right, that the user actually wants to type? So if you type the letters G or O, then maybe the word that the user wants to type is good, or maybe it's Google, right? Or it could be some other word. Or it could be just goo. All right, and there are other applications, but yeah. So how can we implement a set of strings using the data structures that we've covered so far? Right, so we've learned 2 quite efficient data structures, right? We've got an AVL tree, which has a performance of log n in the worst case, right? And we've also talked about hash tables, which have a performance of 0.1 on average, right? And also 0.1 in the worst case, but in the case of hash tables, the average case is the more realistic time complexity. All right, so these are 2 really nice data structures, so why don't we use these? Right, so these data structures are efficient, but in order to search in an AVL tree or a hash table, we need to provide the full string, right? We need to provide the string that we're searching for, and that's not always possible in the applications that I mentioned above, right? So for example, if you want to figure out what possible words could be typed by pressing a certain sequence of keys on a keypad, how do we actually use an AVL tree containing strings or a hash table containing strings in order to figure that out? Right? We can't, because we don't actually know what the string is. Right? So what we would have to do if we had an AVL tree or a hash table is to possibly try every possible string that could arise, right? So for 4663, maybe you would search for the word GMMD, right? That's one possible word. Then maybe you could check GMME and so on, right? Until you've checked every possible word. But that would be quite inefficient, right? Okay, oops. So the other thing is autocompletion, right? So if you've only typed the first, the beginning of the word, right? How can we actually use an AVO tree or a hash table to find all the possible words? Well, there's no easy way to do that. Okay, so yeah, that's the problem with AVO trees and hash tables for these applications. Right, so one possible solution to this problem is to use a data structure called tries. Right, so a trie is a tree data structure, and we use it to represent a set of strings. Right, so for example, we can take all the words in a document and then insert them into the trie. We can take a dictionary of words and store all of those words in the trie. And in this lecture, we'll mainly call them keys. Right? So we'll call the strings keys, or we'll call them words. And a nice thing about a trie is that it supports string matching queries in O of m time, where m is the length of the string being searched for. Right? So if you have fairly short strings, then searching is expected to be quite efficient. Right? And a bit of fun fact, so the word trie actually comes from retrieval, but it's pronounced as try, not tree. Okay, so here is an example of a trie before we get to actually describing more of what it is. So you can see that it's a tree data structure, right? And in this case, each node has only one or two children, but in another trie, some nodes could have more than two children. Right? And we see that each node contains a character, and each key is represented by a path in the trie. Right? So, for example, we have a path that involves the letters A, C, E, right? And that tells us that the word ace, or the key ace, is in the trie. Right? And notice that some of these nodes are marked red, right? And this means that these nodes are finishing nodes, and finishing nodes are used to mark the end of a key. Right? So, for example, ACE is a key that's in the trie because the last letter, the node representing the last letter, is marked as a finishing node. Right? Whereas the word ear, or the key ear, is not in the trie because even though we have a path EAR, right, the last node R is not marked as a finishing node. All right, so you can see that these are the keys that are in the trie, right? So we have ace, we have aces, ape, apes, app, apply, then we've got early, earth, and east. Okay. So, yeah, so here is partly what I talked about before. So in a trie, each link in the trie, so each edge of the trie represents an individual character. Right? So in this diagram, I actually put the characters in the nodes themselves, but what's really going on is that each link represents a character. So this link, for example, here from the root node to the A, or to this node, represents an A, right? Whereas this link here represents an E, this link here represents a C, this link here represents a P, and so on. Okay, and a key is represented by a path in the trie. Right, so for example, we have a path ACE, or ACE, and since this path ends in a finishing node, that means the word ace is in the trie. Right, and I talked about finishing nodes already, so each node can be tagged as a finishing node. Right, and a finishing node marks the end of a key. Okay. And as well as storing keys in the trie, each node can also contain some extra data associated with the key. So for example, if you're using the trie to store words and their definitions, then the extra data would be the definitions of the words. And your keys would be the words themselves. Right, and an important thing about tries is that unlike a search tree, like an AVL tree, for example, the nodes in a trie do not actually store their associated key. Right, so for example, this node here corresponds to the word ace, right, or the key ace. But the node itself wouldn't actually contain the string ace. That's because keys are implicitly defined by their position in the trie. Right? So because this path here involves the links A, C, and E, that means the key corresponding to this node is ace, right? And we don't need to store the word ace in the node itself because it's already implicitly defined. Okay, so that's a little bit about tries. So how would we actually represent tries in code or in C? So first of all, we need to have an idea of what kind of characters could occur in a key. Right? And in this case, you can probably guess that we're assuming that the keys only contain alphabetic characters. Right? So characters from A to Z, and it'll be case insensitive. Right? So we'll just assume that all the keys contain lowercase letters from A to Z. All right, so in each node, we'll have an array of 26 pointers. Right, so struct node star children containing 26 pointers. And each node also has a Boolean to mark whether the node is a finishing node or not. And each node may also contain some associated data. So I've got the type data here, which could be whatever you want. So it could be ints or a string or something else. Okay, so here is an abstract view of a trie. All right, so in this trie, we have the words C, cells, and she, right? So that's because we have a path corresponding to SEA in the trie. We also have a path corresponding to SELLS that ends with a finishing node, and we also have a path corresponding to SHE, which ends in a finishing node. All right, now if we use this representation in order to implement our trie, this is what it would actually look like. Right, so in our root node, in every node, we would have an array of 26 pointers, right? And you might be thinking, that is a lot of memory being used, right? So we'll address that later. Each node contains 26 pointers, and the index of a pointer determines the letter, right? So for example, in the root node, right, we have a pointer at index, pointer at some index, which happens to correspond to S, right? So index 0 would correspond to A, index 1 would correspond to B, and so on. And in this case, we have a pointer at the index corresponding to S, right? One node down, we have two pointers, right? One at index 4, which corresponds to E, and one at index 7, which corresponds to H. All right, and next to each array, so in these nodes, I've added an F here to indicate that these nodes are finishing nodes. All right, so this is the actual representation of our trie. Right, so this is the abstract view of a trie, and this is the concrete representation. Yeah. In this case, all of the other pointers will be null, except for this one. Yeah. If there's a child node, then there'll be a pointer to it. Otherwise, the pointer will be null. Yeah, question.
Why is it that we create, so if you go S, and then it goes NG, but then it creates two separate 26s, could it just combine into that node? So like say, right? So like as in after NG, creates two
Yep.
new ones, and have one with A, E, and L in it?
In that case, I think we might not be able to distinguish whether certain words are in the trie or not, because if we combine these two nodes, right, so that means both the E pointer and the H pointer point to the same node. If we mark the node as a finishing node, then we wouldn't know whether SE is in trie or SH or both. So we need to separate them. Okay. So yeah, that is what the trie actually looks like in the program. Okay, so now let's try and operate on our trie. So how do we actually insert into a trie? Okay, so we're given a trie, and we're given a key to insert. So how do we insert? Well, we're starting at the root node. Right, then for each character in the key from left to right, if there is no child node corresponding to the current character, right, then we create the new node, and then we descend into the child node, right, corresponding to C. Right, and once we've gone through the whole key and we've descended all the way down to a node, then we mark the resulting node as a finishing node, and we insert the data if there is any. Okay, so here is an example. So we want to insert the following words into an initially empty trie. Okay, so when we create a trie, we start off with a root node always, right? And so the first word we want to insert is C, right? SEA. So initially, the root node doesn't have any child nodes, so it doesn't have a node corresponding to S. So what we'll do is we'll create a child node containing, or a child node that's corresponding to S. Right, then from that node, we'll create another child node corresponding to E. Then from that node, we'll create another child node corresponding to A. Right, so we'll get this after we insert C. And we'll mark A as a finishing node. Okay, the next word is shell. So when we insert shell, the root node already has a child node corresponding to S. Right, so we don't need to create a new node for S. But when we get to the next character H, S doesn't have a child node corresponding to H. So we'll create a child node for H, then we'll create one for E, then for L, then for L. Right, so what we'll get is this. Okay, next. So when we insert cell, there is already a child node corresponding to S, right? And from S, there is already a child node corresponding to E. Right? But then there is no child node corresponding to L, so what we'll have to do is create a new node for L, and then another node for the second L. Right? So this is what we'll get. Then we insert shore, so same kind of thing. So the trie already contains a path SH, but then there's no O. So we create new nodes for O, R, and E, like this. Right, and this is an interesting case. So when we insert the word she, there is already a path corresponding to the letters S, H, E. Right? The only thing is the E isn't marked as a finishing node. So what we'll do is we just mark the E as a finishing node, and that's it. All right, so before we inserted she, the word she is not in the trie, right? But because this E is not marked as a finishing node, right? After we insert she, it is now marked as a finishing node. Okay, so that's is how we insert. Okay, so this is what the tree that we get. And we can, yeah, question? Yeah. Yeah, so each of these nodes can have up to 26 children, assuming alphabetic keys. Yeah.
When you showed the concrete example, when you said finishing tries, you gave an empty array for that, right?
Finishing nodes.
Yeah, so how would it point to the finishing node? Let's say you're at like
Okay, so
yeah, so how would it pretty much point to the finishing node? That's my question, because I understand that, let's say you go from E to the next letter, right? How do we know exactly if A will point to the finishing node or an A points to something else as well?
so which node are you referring to?
So let's say we're trying to write sheet or C. So you go S E A, and then
Yep.
A also points to another node and isn't just the finishing node. So how would A also point to another node?
So when we insert the word C into the trie, so first of all we follow the pointer corresponding to S from the root node. Then we follow the pointer corresponding to E from that node. Then if, so when we're trying to insert C, if this pointer here currently points to null, then we would create a new child node and make this index 0 point to it. Right? And then we would mark this node as a finishing node.
And if you try to add C within S,
yep.
we add an S within the array itself.
So if we're trying to add the word C, so plural, SCAS, then we would go over to this node, right? And we would add another child corresponding to the letter S. Yeah, so finishing node doesn't necessarily mean that it's a leaf node. A finishing node could have other children. Yeah. So like in this example here. Okay. So now we can try and implement insertion. Right, so following this process, but we're going to do it recursively. Okay, so here's try.c, and I've already implemented try new. So inside this function, we simply malloc a root node and then return it. Right, and we're using calloc. That's because it nicely initializes all the pointers to null, right? And it also marks it as not a finishing node. All right, so how do we insert into a trie? So this function takes in a trie, right? Initially, this will be the root node, and it takes in a key, and it returns a trie, right? It returns the trie itself. Okay, so first of all, if the trie is empty, right, that means we need to create a new node. Right, so that means we're going to, do I have a new node function? No, I don't. All right, so what we'll do is we'll simply malloc a new node. So t equals malloc, or actually we'll use calloc, size of star t, okay, and this creates a new node. And we're not going to return it because we might need to create more child nodes under this node. Right, so now what we'll do is we'll check if the key is empty, right? So if we've reached the end of the key, so if the first character is a null terminator, then we'll mark t as a finishing node. Right, so t finish equals true. And in this trie, we don't have any data to store, so yeah. Okay, and now, so if the key actually has multiple characters, or this isn't the last character in the key, then we might need to traverse further down the trie, right, and insert and then create more nodes. So what we'll do is, first of all, each character of the key is a letter between A and Z. It's a character between A and Z. So we need to convert that to an index between 0 and 25. Right, so what we'll do is we'll go calculate the index here. Right, so key 0 is the first character in the key, and we'll subtract off A. Right, so if we have a letter between A and Z, now we'll have an index between 0 and 25. Okay, so this is the index corresponding to the first character in the key. So what we'll do is we'll recurse into that subtree or subtrie, and then insert, giving it the rest of the key, right? So everything in the key except for the first character. Okay, so the way we do that is T our children I. So T our children is an array of children, and we recurse passing it T arrow children I, and we pass it the rest of the key, right? So we want everything in the key except for the first character. So the way we do that is we pass it the address to the second character of the trie of the key. Right, so ampersand key 1. We'll do that. Okay, and then we return T. Right, so this should, so hopefully this works. Right, so in my test program, I've created a new trie, and I've inserted all of these keys. Right, so C, shell, cell, shore, and she. And I also have a program, a function for printing a trie. Okay, so here's the function. It's a bit ugly, but it'll print it nicely. Okay, or pass through this function will call itself. Oh yeah, I forgot that I need to return. Right, so if we reach the end of the key, then we should return T. Here. Okay, so now let's see if it gives us a trie. Yep, so here we see the trie printed out in this form. So we have a root node, and the root node contains the child S, right? And the S contains the children E and H, right? And the E contains the child A, which is a finishing node, so that tells us the word C is in the trie. Right? We also have the word cell, right? S-E-L-L. We also have the word shell, S-H-E-L-L. We have the word she, which is S-H-E, and E is marked as a finishing node. And we have the word shore, right? S-H-O-R-E. Okay, so that's how we insert, and oops, here's the pseudocode for it. All right, so we're given a trie, we're given a key, and we're given some data. So in my implementation, I didn't have any data, so it was just trie and key. But if the trie is empty, then we create a new node and assign it to T. Right? But importantly, we don't return because we might need to create more nodes under this node. Right? And now if m is equal to 0, so m is the length of the key that we're given. So if m is 0, which means we've recursed and we've reached the end of the key, then we set T to be a finishing node. Yeah.
What was the
So we inserted 5 keys in the program. So the first key was C. Yeah, then we inserted shell, then cell, then shore, then she. So we could actually print out the trie after every insertion to see what we get. But yeah. Okay. If the key isn't empty, then we get the first character of the key. Right? And then we also have some notation here that means just get, slice off the first character from the key. And what we do is we recurse, pass it the child corresponding to the first character in the key, so T arrow children first, then we pass it the rest of the key, then we pass it the data. Okay, and you can write this iteratively, so one exercise would be to try and do that. Okay, so that's insertion. So how do we perform a search? Right, well, search is very similar. Right, the only difference is that we're not creating any new nodes. We just want to check if there is a path in the trie corresponding to the letters in the key. Right, so we start at the root, and for each character in the key from left to right, if there's no child node corresponding to the character, then that means the key doesn't exist in the trie. Right, so we return false. Otherwise, if there is a child node corresponding to C, then we descend into the child node, and we do this for every character. Right. And then, if the node that we end up at is a finishing node, then we return true. Otherwise, we return false. Right. So just because there is a path in the trie corresponding to the characters in the key, that doesn't mean the key exists. Right. The last node in that path has to be a finishing node. Okay, so with that, there are some different cases, right, for searching. So here are some examples. Right, so suppose we have this trie and we are searching for the key early. Right? So in this case, there is a path corresponding to the letters E-A-R-L-Y, and the Y is a finishing node. Right? So that means early is in the trie. Right, next example. So suppose we're searching for the word apple. Right. So that means we try to find a path corresponding to A-P-P-L-E. So we go to A, then we go to P, then we go to P, then we go to L. But L doesn't have a child node corresponding to E. Right. So that means apple is not in the trie. Okay. All right, and last case is searching for the word ear. Right, so when we search for ear, we see that the root node has a child node corresponding to E, the E has a child node corresponding to A, and the A has a child node corresponding to R, and this is the node that we end up at. Right? But the node isn't marked as a finishing node. So ear is not in the trie. So let's try and implement search. Okay, so test try.c. Okay, so let's remind ourselves of the process. Right, so first of all, if the trie is empty, right, then that means the key isn't in the trie, so we return false. Okay. Otherwise, if the key is empty, so if key 0 is the null character, then that means we've reached the node corresponding to the key, and all we need to do is check whether this node is a finishing node or not. So return T finish. All right. Otherwise, we need to grab the first character from the key. Right, so int also char first equals key 0. Right, and we need to convert this character to an index between 0 and 25. So we need to say, int I equals first minus a, and then we recurse on the corresponding child node. Right, so return try search t children index I, and we pass it the rest of the key, so the address of the second character of the key. Okay. So now, this program doesn't actually call try search, but we can add a couple of calls. So let's assert that the word C is in the try, right? And let's assert that the word shell is in the try, and let's remove the word she, just so we can test this case where there is a path, but the node isn't marked as a finishing node. Right? So we'll assert that the word she is not in the try. Right, and what else do we want to search for? Let's search for the word sand. Right, so we know the word sand is not in the try. Right, and let's see if we pass those tests. Okay. Okay, so no errors, so we pass the tests. Okay, and yeah, here's the pseudocode for searching. Right, so if t is empty, then that means the key doesn't exist, so we return false. Otherwise, if the key is empty, right, then that means we've reached the node that we've been searching for, and we simply check if it is a finishing node. Right, so return tFinish equals true. Otherwise, we grab the first character from the key, and then we also create a string that is just the key except with the first character removed, and then we recurse on the child corresponding to the first character. Okay, and we pass it the rest of the key. Right, and this can also be implemented iteratively, so you can try and do that. All right, so we've covered insertion and search. So let's talk about deletion. Right, so deletion is a little bit trickier. So one simple way of implementing deletion is to just find the node corresponding to the given key. So you can do that using the methods that we covered above with searching, and simply mark it as a non-finishing node, right? Just unmark it. But the problem with this is that it can leave behind dead branches, right? And these are just branches that don't contain any finishing nodes, and they just waste memory, right? Because if a branch doesn't have any finishing nodes, then there's no point for the branch to exist. Right, so here's an example. So suppose we have a trie consisting of the words C, cell, she, shell, and shore. If we delete the word shore by simply traversing down to the node and marking it as not a finishing node, then we end up with this branch here that doesn't contain any finishing nodes, right? And there's no point for us to have this branch. Okay, so what we do is we need to make sure to clean up this branch, right? So what's the process? Well, first of all, we find the node corresponding to the given key. Right, and if the node doesn't exist, then that means the key doesn't exist, so we don't do anything. And once we've found the node, then we mark the node as a non-finishing node. Okay, so like this, so we just mark the E in this case as a non-finishing node. And now, in order to clean up the trie and make sure that we don't have any dead branches, while the current node is not a finishing node and it doesn't have any child nodes, then we delete the current node, or we free the current node, and we move up to the parent, right? And we just repeat that until either we reach a finishing node or we reach a node that has another child node. Okay, and this part is handled recursively, okay, because nodes in our trie, the nodes don't have pointers to their parents. Right, so we handle this cleaning up part recursively. Okay, so here are some examples of deleting from a trie. So here, suppose we want to delete the word ace, right? Then we find the node corresponding to the word ace, which is this node over here, and we just mark it as a non-finishing node, right? And that's it. We don't need to remove this node because the node has another child, which is a finishing node. So if we remove this node, then what's going to happen to the word aces, right? Yeah, so that's all we do. Next example is suppose we delete the word apply. Right, so first we're going to find the node corresponding to the word apply, right? And then we're going to mark this node as a non-finishing node, right? But then that's going to create a dead branch over here, right? So what we'll do is we would delete this node y, right? Then we would go and delete the node l, and then since p is a finishing node, we would stop there. So here's the result. We delete the nodes corresponding to apply and also APPL. Right. Okay, here is another example. So suppose we want to delete the word earth. Right. So first we would find the node corresponding to the word earth, and we would mark this final node as a non-finishing node. But then since this node doesn't have any child nodes, we should remove it. Right, then we go up to T. Now since T is a non-finishing node and it doesn't have any child nodes, now that we've deleted H, we also delete this node. And once we go up to R, R has a child node L, right? So we stop, we don't remove R. Right, so this is the result that we should get. Okay, so let's try and implement deletion. Now here's the pseudocode. Right, so if the trie is empty, there's nothing to delete, so we simply return the trie itself. If the key is empty, then that means we've reached the node corresponding to the original key. So we mark the node as a non-finishing node. Right, so T arrow finish equals false. Otherwise, if the key is not empty, then that means we need to continue searching for the node corresponding to the key. Right, so we grab the first character from the key, we grab the rest of the key, and then we recurse to find that node. Okay, and finally, we perform the cleaning up process. Right, so after we've set the node as a non-finishing node, or after we've recursed on our subtree, then we clean up. So if the current node is a non-finishing node, so if tFinish equals false, and T doesn't have any child nodes, then we return null, right? Otherwise, we just return T. Yeah, so you would free it. Okay, so let's try and implement this. All right, so remember, so the first thing we do is check if the trie is empty. So if the trie is empty, then we just return it. But otherwise, if the key is empty, so key 0 equals the null character, then that means we found the node, so we set t finish to false. Right. And otherwise, we grab the index corresponding to the first character in the key, so key 0 minus a, since we're dealing with alphabetic strings, and we recurse on the child corresponding to that first character. Okay, so t children index I equals try delete t children index I, and we pass the function the rest of the key. Okay, so ampersand key 1. Okay, and after we've recursed, we now perform the cleanup. Right, so so this part over here is not so easy to implement, right? We have to check if t has no child nodes, which means we need to make sure that all the pointers in the array are null. Right, so we may need a loop for that. So bool has child node equals false. Then we iterate through the array. Okay, so for I from 0 up to alphabet size, if t children is not null, then in fact we can just return t, right? And we don't need this boolean. Right, so if we've looped through all the pointers and all of them are null, then we can free t and return null. Okay. Okay, so now let's test our function. Okay, so we'll re-add the word she to our try, and we'll remove these tests. All right, so I'm going to print out the try after we've inserted all of these keys, and let's try removing the word c. All right, so try delete tc. Right, and we'll then print out the try after we have deleted it. Okay, so we run the program now. Okay, so here is the try after we've inserted all of the keys. Right, and after we remove the key C, notice that the node A is now gone. Right, so we have, before we had SEA, and now we just have, now L is the only child of E. Okay. All right, so that means we've performed the cleanup successfully. All right, so let's see if there is another key we can delete in order to test this. All right, so let me go up to the try. Where was my example? Yeah, here. So here is the try, actually. So let's try and delete the word sure, right? Because this tests another kind of edge case. So let's go here again and delete sure. Okay, so we delete that. Right, now we no longer have the nodes corresponding to O, R, and E. All right, so that's gone now. So it seems like our function works. Okay. All right, so what is the time complexity of these operations, right? So all of these operations perform very similarly, right? They simply recurse down the trie corresponding to the characters in the key. So if the key has m characters, so m is the length of the given key, then that means insertion, search, and deletion are all OM in the worst case, right? Because we need to examine at most m nodes in the trie. Okay, but as well as time complexity, space complexity is also something to consider, because we saw how much space a trie takes if you use a very simple representation where you have just an enormous array of pointers. Okay, so standard trie, or trie implemented this way, takes up O of nr space, where n is the total number of characters in all the keys, right, and r is the size of the underlying alphabet, for example, 26. Okay, so standard trie takes up a lot of space. So what are some methods to save space? And we'll talk about this after the break. Right, so we'll come back in 5 minutes at 3:05. Right, and if you want, you can come and grab some candy. Okay, so let's continue. So the problem with the simple trie representation that we talked about earlier is that it consumes an enormous amount of memory. Right? If we're dealing with alphabetic keys, then our node would contain 26 pointers, right? One for each of the letters. And if you do the math, then that's 208 bytes. Right? So each of your nodes would be at least 208 bytes large, which is a lot, right? And in fact, if your keys are allowed to contain any ASCII character, so not just alphabetics, but maybe digits and punctuation, then that would be 128 pointers, right, which is even larger. So yes, and most of these pointers would be unused, right? Even if the trie contains many keys, because at the top of the trie, maybe a lot of the pointers would be used because you have lots of different words starting with different letters. But as you go further and further down the trie, you'll be using less and less or fewer pointers. Right. Okay, so what are some ways that we can reduce our memory usage? So there are different representations that we can use instead of just having an array of 26 pointers. So one is to use a linked list to store our child nodes instead of an array. Right? And we'll just use this linked list to store just the child nodes that we want, right? Or just the child nodes that exist. Right? Another way in order to reduce memory usage is to do something called alphabet reduction. And what this means is we take each character, break it into smaller chunks. So for example, if we have 8-bit characters, then what we can do is break it into two 4-bit chunks, right? And treat these chunks as the characters instead. So instead of having an 8-bit character, we have 4-bit characters. And that means each node requires fewer pointers, right? Because with 8 bits, you have, if you're dealing with ASCII, then that's 108 possible pointers. But if you break the character up into 4-bit, 4-bit chunks, then the number of possible values for each of these chunks is 16, right? So each node would contain only 16 pointers instead. All right, so let's look at the first variation. So one technique is to have each node store a linked list of its children instead of an array of pointers. All right, so here is the concrete representation. Right, so we have our trie node. Right? Each trie node contains a pointer to a linked list, right? And I've called each of these linked list nodes struct child. Okay, and each trie node also contains a Boolean to indicate whether it's a finishing node or not, and some data. Okay, and each of these linked list nodes contains a character, right? So when we were looking at the array representation, right, the characters were implicitly defined by the index, right, of the array, right? So index 0 referred to character A, index 1 referred to character B, and so on. But since we have a linked list now, we need to actually, or we need to store what character the node actually refers to, corresponds to. Right, so each of the child nodes contains a character, a pointer to the trie node, right, and also a pointer to the next node in the linked list. Right, so instead of this representation here, where we have an array and a pointer at indices 4 and 7, right, we would have this kind of representation where this is our trie node, and this trie node contains a pointer to a linked list, in which this one contains E and H, and each of these two nodes contains pointers to trie nodes. Okay, so consider this trie here. So this is what it would actually look like if we used that representation. Right, so each node contains a linked list of its children, and each of these linked list nodes contains a pointer to a trie node. Okay. Yeah, and this is pretty complex, but also what you might notice is that there's some redundancy here, right? Because for each of these linked list nodes, we always have a pointer to a trie node, right? So for example, this node here, A, contains a pointer to this trie node, this pointer B, or this node B contains a pointer to a trie node, this D contains a pointer to a trie node, right? This N contains a pointer to a trie node, and so on. Right, so the question is, why don't we just combine the linked list node and the trie node like this? So instead of having two separate structs, right, where one is a trie node and the other is a linked list node, instead we just have a single node which contains a character, a pointer to its first child, so struct node start children, a pointer to its sibling, right? So a sibling is just another node on the same level, and we also have a Boolean to indicate whether the node is a finishing node or not, and some data. Right? And now this is what the representation would look like, right? Which is much simpler. Okay, so here we have two, each node has two pointers, and I've sort of drawn them differently to highlight the difference. Right, so the solid lines, or the solid pointers, right, so each of these is a pointer to the first child of the node, right? So, for example, for this node A, the children of A are N and T, right? But the node itself only contains a pointer to the first child, which is N. Right? These dotted pointers are pointers to your siblings, right? So, for example, the children of the root node are A, B, and D, and this node contains a pointer to the first child, which is A, and in order to get to the other children of the root node, you need to follow these sibling pointers, right? These dotted lines. Yeah. So it is nice to sort them in order. Yeah, or it depends on your implementation. Yeah, but having them in order is nice. Okay. Yeah, so this is our representation now, and this is a binary tree representation, right? And it's called left child, right sibling. And that's because the left pointers, or in this diagram, the pointers going downwards, point to the first child, whereas the right pointers, or the pointers going across in this diagram, point to siblings, right? Point to a sibling. Right, so suppose we want to search for the word bow, so B-O-W. So how do we do that? Right, well, starting from the root node, we need to see if we have a child corresponding to B. Right, so what we'll do is we would go to, we'll follow the child node to A, and then we would follow the sibling nodes to see if there is a node containing B. Right. So we'll go to A, and A has a sibling containing B, so that means that the root node has a child corresponding to B. Right. Now from B, we want to see if B has a child node corresponding to O. Right. So we would follow the child pointer of B. That takes us to the first child, which is E, and then we would follow the sibling pointers to see if there is one corresponding to O. Right. So we find it, and then we need to see if O has a child node corresponding to W. So we follow the child pointer of O, and the first child happens to be W. So we found the word bow. All right, so how well does this representation perform? Well, first of all, it does use much less space, right? And that's because each node contains just one extra pointer to its sibling, right? So instead of having 26 pointers, now we only have one extra pointer, or we have 2 pointers here, but reduction from 26 to 2 is quite nice. Okay, but of course this is at the expense of running time. So when we search for, when we want to check if a node has a child corresponding to some character, we need to follow the child pointers of the first child and then follow the sibling pointers. Right, so that means we have to traverse up to alphabet-sized nodes before actually reaching the desired nodes. Okay. Yeah, okay, so here is another technique, and this is called alphabet reduction. So one example of alphabet reduction is to take each 8-bit character and break it into 2 4-bit nibbles. All right? And nibbles is a real term, and you can look it up. It actually means 4 bits, 4 bits value, I think. Okay, and the benefit of alphabet reduction is that it reduces the branching factor, right? So that means reduces the number of pointers in each node. All right, so here is an example of alphabet reduction. Suppose we want to insert the word C, like S-E-A. So what we'll do is we would break it into 4-bit nibbles. Right, so we know that S is the ASCII representation of S is 0110011. So we break it into 2 4-bit nibbles. So the first one is 0111, and the second one is 0011. Right, for E, it's 0110, then 0101, and for A, it's 0110 and 0001. Right, so now, instead of actually inserting the word C, we insert the following word, which just consists of these 6 nibbles. Okay. All right. So how well does this variation perform? Well, the representation does use much less space, right? So instead of storing up to 128 pointers in each node, now we only store 16, right? Because if you have 4 bits, right, then the possible values for this nibble is between 0 and 15, right? So 16 possible values. So it uses less space, probably more space than the previous variant that we talked about, which is which only needs only adds 2 pointers to each node. But it does perform slightly better in terms of time, right? So the path to each key is twice as long, right? Because you need to traverse twice as many nodes. Okay, so that's another variation. Now, another way to implement tries is something called a compressed trie. So in a compressed trie, each node contains possibly more than 1 character, and the way we create a compressed trie is we take an existing trie and then we merge nodes that don't branch. Right, so I'll show you an example here. So suppose we have this simple trie. In order to compress it, we look at sequences of nodes that don't branch, for example, AR, and we merge them together. Right. And another sequence of nodes that don't branch is LL, right, in the word bell. So we would merge these 2 nodes together, and now we have a single node containing LL. Another example is ELL here in the word cell. So we would take these 3 nodes and merge them into a single node that contains ELL. And here's an interesting example. So we have a sequence of nodes here, TO, that don't branch. Right? Well, T doesn't branch, but O does. But that means we can combine T with O, right? And this gives us a node containing TO. And it also branches off into C, K, and P. Okay, so yeah, that's another variance. Question?
With compressed tries, does that mean if you wanna, does that mean you can only compress once and then can't use it again, or would you have to like uncompress and then recompress it?
Yeah, so the assumption behind compressed tries is that like after you create the try, you won't be inserting any more words, because yeah, inserting after you've compressed it gets kind of hairy. Yeah, because that means you might have to uncompress some nodes. Yeah, so for example, if you want to insert the word bin, bill, yeah, for example, yeah, so you go B, I, now I is merged with D, so you'd have to unmerge it so that you can add LL, yeah. Okay, so that's compressed tries. Okay, so now we're going to look at just a few applications of tries. Okay, so one simple application of try is to make finding words more efficient. Right, so suppose you're looking through a document and you frequently need to find different words. Right, so one possible way to speed this up is to pre-process it by storing all the words in a try. And then for each word, we store the location of all of its occurrences as the extra data. And when the user searches for a word, instead of scanning the entire document, which might take a while, we can just query the try. Right? Remember, a try has complexity O of M, where M is the length of the word being searched. Right? So that's much better than scanning the entire document. Right, so here is a small example of that. So suppose this is our document. So we've got a bunch of words here, and not all of these words are in this try, but you can see that if we want to search for the word cell, let's see. No, let's suppose we want to search for the word stock. Right? Then what we would do is we would search for the word stock in the try. Right? So STOCK. Right? And at this node, we would also store additional data which tells us where the word appears. Right? So in this node, we would have the indices 17, 40, 51, 62. That tells us the word stock appears at these indexes. Right? So 17, 40, 51, and 62. Okay. So that's one application. Another application is predictive text, which I talked about at the beginning of the lecture. Right, so if you have a keypad and a series of button presses, where each button can represent multiple letters, then we want to find all the possible matching words. Right, so if you have a different data structure, let's say an AVL tree, and you've stored all the words in there, right, if you're given a series of button presses, how do you actually search for the possible words? Right? It's hard to do it if you have an AVL tree, because in order to search in an AVL tree, you need to give it a word, right? But what word do you search for? Well, that's the problem. And same for a hash table, right? If you don't actually have the word, then how do you search? Right? You'd probably need to generate all the possible words that could exist based on the button presses and then try all of them, which would be inefficient. Okay, so that's one thing that tries have over AVL trees and hash tables. So let's try and implement text prediction. So in this program, I have an array here just corresponding to the keypad. Right, so 0 and 1 don't actually correspond to any letters, but 2 corresponds to the letters A, B, C, 3 corresponds to the letters D, E, F, 4 corresponds to the letters G, H, I, and so on. Okay, and here, so we need to have a trie that stores all the possible words, right? So all the words in the language. Right? So what we'll do is just insert these words, just to test. So for int I equals 0, I less than 12, there are 12 words in this array. We'll just insert it into the trie. So T keys I. All right, and now we want to see what possible words match this series of button presses, 4, 6, 6, 3. Right, I think this was what I showed earlier. Right, so 4, 6, 6, 3 could be interpreted as the word good, home, right? So H-O-M-E, hood, H-O-O-D, or hoof, H-O-O-F. Right, so I've inserted all of these words into the trie, and we want to see now if we can retrieve those words. All right, so our function predict takes in a trie, it takes in the keypad, which is the array that I have shown here, and it also takes in the sequence of key presses. Okay, so 4, 6, 6, 3. All right, so what we want the function to do is to print out all the possible words, right? And the problem is, since the nodes in the trie don't actually contain the words themselves, right? When we're traversing through the trie, we need to build up the string as we go. Okay, so what we'll do is we will create an array in order to store the string or the key as we go. Okay, so key, and let's just initialize it to 100. Kind of a hacky way to do it. All right, just initialize it to null. And we're going to call a recursive helper function that takes in the key. Okay, so let's call it do predict. We pass in the trie, we pass in the keypad, we pass in the key presses, we also pass in the key, and we also pass in the index that we're up to in the key, right? Because the first when we go down to the first node, we would add a character at index 0, right? Then when we descend into another node, we add a character to index 1, right? And so on. Okay, so here is our recursive helper function. And here's our key, and here's the current index in the key. Right, so a lot to take in, but this function is recursive. So first of all, let's deal with the base case. Right, so if the trie is empty, then we just return because there's nothing to print. All right, And now what should we do? Well, another possible base case is what happens if we've processed all the key presses, right? And now we're at the node that we want. Right, so if key presses, so if this array is empty, or if the first character is a null character, then let's check if the current node is a finishing node. All right, so T our finish. Right, then we want to print out the word. Right, so printf %s, and we print out key, right? Because we've been building this array up with characters as we recurse down the trie. Okay, so printf key, and then we should just return, right? Because we know that we don't need to descend further down the trie. And actually, we should just return here instead of in the if statement. All right, so now we need to process the current key press, right? So that's the first key press in this array. So let's say key press equals key presses 0. Right, and this key press is a character between, if we go up here, it's going to be a character between 2 and 9. Okay, so in order to index into this array, we need to convert the character 2 into the number 2. Right, so the way we'll do that is keypad index. So first of all, let's subtract 0. Right, that means the character 0 will turn into the number 0, the character 1 will turn into the number 1, and so on. So key press minus character 0. Okay, and now each key press could correspond to multiple different characters. Right, so what we need to do is to loop through the string, right, corresponding to the key press. So if the key press was 2, then we want to loop through A, B, and C and try all of those. If the key press was 7, we want to loop through P, Q, R, S. So let's add some code to do that. Okay, so let's see. So for int j equals 0, j, so keypad index. So while this thing is not the null character, right? So we're looping through one of these strings. So for each of those characters, so now we have a particular character. So char c equals keypad index j. All right, so now c is one of these characters. Right. So what we want to do is recurse into the trie corresponding to that character. Right, so do predict t children c. Right, and let me first think. So we need to actually minus a, right, in order to give us an index between 0 and 25. Right, so do predict t children c minus a. And we just pass it the keypad, we pass it the key presses, we pass it the key, and we increment I by 1. Right? But before we recurse, we actually want to store the character C in the key, right? Because we're building up the key as we go. So key at index I, so we'll store C at index I, and then we recurse and pass it index I plus 1 so that in the recursive call, we store the next character at the next index. Okay, and yeah. It is I, because I is the index that we're up to in the key. Whereas J, we're using J to loop through one of these. Okay, so I'm curious to see whether this works. Oh yeah, so there is one problem. So key presses, right, we need to actually pass it. Key presses except we get rid of the first key press, right, because we've already processed this. So we do the same thing that we did when we inserted into a trie, and we pass it the address of the second character, right, in this string. Okay, so now we need a function prototype. Okay, and yeah, I'm curious to see what this will give us. So, okay, so keypad. Okay, so there's just a typo. Yeah, it's supposed to be all lowercase. Okay. Yep. Right, and then when we try to run it, it gives us the words that we want. So good, home, hood, and hoof. Right, those were the words. So what we did was, we had inserted all of these words, and now it gives us the words that correspond to the key presses 4663. Okay. Cool. So yeah, that is predictive text. Now, you could go and have a look at the other examples. So autocomplete is an interesting application that you might want to try yourself as an exercise. Right? So given the first part of a word, print out all of the words that could be, could arise from extending the words or extending the word that has been typed in so far, right? Yeah. Okay. Yeah, and that is the lecture. And that is all the content for the course. So next week, we'll go through a review of the course next Monday, and we'll also talk about the final exam. And Wednesday, we probably won't have a lecture. We just have the Monday. Yeah. Yeah. Probably not practically, just the theory. Yeah. Okay. So yeah, I'll see you guys on Monday. Have a good week. Oh yeah, and the revision session is happening right now, so you could go to that if you want. For this course, yeah. It's in CLB 8, I think. I think so, yeah.